Good morning, everybody, and welcome to this second lecture that is dedicated to ozone, the basis and the application of ozone to water treatment. So first of all, I would like to know how many of you are working with ozone or think they are going to work with ozone in the near future? Nobody. Apart from Manu, that is, yeah, okay. Because for you all that are working or are going to work with ozone, this is going to be very basic. But if you have some question, you can ask me later, or during the coffee break, or through my email. Okay, so feel free. So as Alessandra said, I'm Eva Rodríguez. I'm not Swiss. I'm currently working at the Laboratory for Water Quality and Treatment of the EPFL in Switzerland. As a research collaborator of Professor von Guntem. But previously, I have worked for more than 15 years with Professor Fernando Beltrán. Both of them, I think, are leaders in the field of ozone. So let's go. Ozone is as you all know, ozone is an allotropic form of oxygen that has been used for many years in drinking water treatment. And during the last decade, is starting to be used also for the treatment of tertiary wastewater. Has increased the use of ozone in the tertiary treatment of municipal wastewater. It's a very high oxidizing and disinfectant agent. And in the table, you can see that its oxidation potential is very high, 2.07. So once ozone is dissolved in water, the oxidation capacity of water increases. And once in water, ozone can act through two different ways. The direct reaction, so molecular ozone reacts directly with the organic or inorganic present in the water, or the indirect reaction that is initiator, but a substance that is called initiator, that promotes the decomposition of ozone into hydroxyl radicals. This decomposition can be initiated by hydroxyanion, through the mechanism that is given from equations 1 to 6. This is the Stirling, Onye, and Buehler mechanism. In this mechanism, ozone is decomposed, reacts with hydroxide anion, and superoxide radical is. So there is an important role of superoxide radical here. Cesar, this is dedicated to you. Because the formation of superoxide radical leads to the formation of ozonide radical anion through the reaction 4. Superoxide and ozone reacts very fast. And the ozonide radical anion is the one that leads to the formation of hydroxyl radical. Okay? In fact, an initiator of the decomposition of ozone into hydroxyl radicals is that species or compounds or substance that can on its reaction with ozone can lead to superoxide. Yeah? We will back to this aspect later. Okay, so we can use ozone in water for many different purposes. Some of them have been used only at lab at bench scale, probably will not be feasible at industrial scale, but most of them are here. We can use ozone to remove odor and color or taste. What we do is to oxidize the compounds responsible of these organoleptic properties or to avoid their formation. To oxidize iron 2 and Mn2 to insoluble oxides that later are easily removed by flocculation, coagulation, sedimentation. To improve flocculation, allowing lower doses of coagulants. To decrease, this is a very, very important aspect, to decrease the potential of formation of chlorinated GBPs, disinfection byproducts in drinking water treatment. This is why it's so important, it's so famous, the use of ozone in drinking water treatment. So when we use ozone, the formation of THMs, haloacetic acids, or haloacetonitriles decrease enormously. Also to reduce the chemical oxygen demand of the water by oxidizing the organics present, to increase the biodegradability, transforming non-biodegradable compounds in more biodegradable ones, to remove micropollutants. Probably many of you are centered in micropollutants from the wastewater, and a very important aspect, not only is a very efficient oxidant, it's a very powerful disinfectant. I don't know if you are familiarized with the CT concept in disinfection. Yeah, no? Well, CT is the mathematical product of C times T. C is the concentration of the disinfectant in milligrams per liter, chlorine, ozone, chloramine, whatever. And T, the time in minutes that this disinfectant is in contact in water. So in this table, you have a summary of the CT values of CT ranges for different disinfectants, free chlorine, that is the sum of hypochlorous acid and hypochlorite, chloramine and chlorine dioxide and ozone, for the inactivation of 99% of different microorganisms at 5 Celsius. So if we compare, I'm a bit lost. If we compare the values corresponding to ozone, the CT values or ranges are much lower than for the rest of disinfectants. So it means that the lower the CT, the higher the disinfectant capacity is. So let's see an example. Let's imagine that we have a residual value of 0.5 milligrams per liter of chlorine or ozone in water at pH 7. And we have to determine the minimum contact time that we need to obtain a 99% of reduction of E. coli or Giardia lamblia cyst. In the case of ozone, for E. coli, we look for E. coli with ozone, 0.02 the CT. Since our residual concentration is set to be 0.5, we obtain that the contact time in seconds will be 2.4. Doing the same for chlorine, it will be 6 seconds. Okay, much better for ozone, less time, but there are more differences for other microorganisms, as it is the case of Giardia. While with ozone and 0.5 milligrams per liter, 72 seconds will be enough. In the case of chlorine, almost 6,000 seconds will be needed. So have you understood the meaning of the CT? Yeah? Let's move to the... Okay, but are there any disadvantages of the use of ozone? Of course there are. One of them is mainly related to drinking water, is if there is a high concentration of bromide in the raw water. During the ozonation, bromide is formed, and is probably carcinogen to humans, so maybe ozone is not a feasible option. Another more important disadvantage is that ozone is very unstable, has a very short life. So it is formed from oxygen and falls back to oxygen after a while. It implies that it must be generated in situ. You cannot pick up the phone, please take me a balloon of ozone, no. So you have to obtain in situ and cannot be used as a final disinfectant. So you can disinfect your water, but if you want to have a residual one through the distribution system and so on, you have to add chlorine or monochloramine or chlorine dioxide. And the cost of the production of ozone is high because the process of extension is very high, very energy consuming. So how is ozone produced? Let's see first how it is naturally produced, how it's produced in nature. I'm going to drink a bit. Sorry. So as you know, there is a bad ozone, the one that is formed at the troposphere or ground level due to the interaction between different air pollutants and sunlight. And the good one, the good ozone, that is that forms the ozone layer. This ozone layer acts as UVB and UVC filter and makes life on Earth possible. This good UV, or this good ozone, is forming in the stratosphere from the photolysis of oxygen of wavelengths lower than 240 nanometers. This is the Chapman mechanism, the simplified mechanism of ozone production and destruction. So in the first reaction, represents the photolysis of oxygen at wavelengths lower than 240, with the formation of atomic oxygen. This atomic oxygen recombines through reaction 2 with a molecule of molecular oxygen, and in presence of an inner species that can be nitrogen, for example, just to dissipate the excess of energy, ozone is formed. So through reactions 1 and 2, ozone is formed, and through reactions R3 and R4, ozone falls back to oxygen. In the reaction number 3, the photolysis, in this case, at wavelengths lower than 320 nanometers, led to the formation of oxygen and atomic oxygen, and then through reaction 4 to oxygen. So there is an equilibrium in the stratosphere between the formation and the separation of ozone. And this equilibrium can be altered by the presence of substances that react with ozone, such as this famous CFC, you know. Okay. Let's see these wavelengths that we have indicated here. So if you are not working with ozone, but you are working with lamps that emit at wavelengths lower than 240 nanometers as vacuum UV lamps, and you are feeding air or oxygen, you can produce ozone. Take into account. And if you are working with ozone and lamps that emit at wavelengths lower than 320 nanometers, you can photolyze ozone with formation of atomic oxygen. But whereas in air, it will be, so through reaction 3. But atomic oxygen in water leads to the formation of hydroxyl radical. In fact, when Manu, I suppose he will explain on his poster, ozone absorbs at wavelengths higher than 320 nanometers, but its molar extinction coefficient is very low. But if the intensity of your lamp with higher wavelengths is very high, you can decompose ozone into hydroxyl radicals in water. Okay. Apart from the Chapman mechanism forming the ozone layer, ozone is also naturally formed during thunderstorm. The electrical discharge is very high, and it's capable of splitting oxygen into atomic oxygen, then recombine with molecular oxygen to form ozone. So, looking at how ozone is formed in nature, we can simulate these two routes to produce it artificially, and it is what we do. We can obtain ozone by vacuum UV photolysis using normally 185 nanometers centered lamps, but this system of ozone production is only used at lab scale, or by electrical discharge that is used both at lab and industrial scale. Okay, so this will be a general scheme of an ozonation process. We have our gas inlet that can be pure oxygen, synthetic air, or even atmospheric air previously filtered and dried. The gas feed, the gas mixture, air or oxygen is fed to the ozonator, that is normally water or air cooled to dissipate the heat. And depending on the electrical discharge, the voltage applied, and the amount of oxygen in the inlet, we will obtain more or less amount of ozone in the gas outlet. So the amount of ozone at the outlet, in the gas outlet, the partial pressure of ozone in the gas outlet, will depend on the content of oxygen in our inlet and also in the voltage applied in our ozonator. Okay, we have obtained ozone. We have a gas stream that contains some amount of ozone, and it now must be transferred from the gas to the water. So with this purpose, the reactors are designed to favor the mass transfer from the gas to the liquid, and to allow, at the same time, to allow the maximum residence time in the reactor. So this is one example of ozonation reactor, where the ozone, the gas inlet, is fed through the bottom, through diffusers, and the water put in contact with the gas in countercurrent. The lower, the finest the bubbles of air ozone are, the higher the mass transfer coefficient and the higher the retention time. Okay, remember, ozone is a gas. As any gas, its solubility decreases with the temperature. In fact, there is a direct relationship between the partial pressure of ozone in the gas phase and in the liquid phase that is given by the Henry law that probably you all know. This Henry constant of equation number 10 depends on the temperature, on the ionic strength, on the pH, so you can find several very nice correlations in the literature to obtain the Henry constant. And finally, at the outlet of our reactor, we have to include a distractor, an ozone distractor, because ozone is a very harmful species. So normally this is a catalyst that composes the ozone that is left, that is still remaining in the gas outlet. So, just a moment to tell about some things about that I think are important if you are working at the lab with ozone. So first of all, please work safely. So check there are no leaks of ozone in your installation. So check tube connections, check the inlets and outlets. You can do it using ozone sensors or even wetting a lab paper with potassium iodide. If you see that the paper turns yellow or orange, it's because you have a fuge of ozone. Also use compatible ozone materials, such as Teflon, that is PTFE, or glass. We have been used, just in case, we have been used diffusers that were made of stainless steel. And during the ozonation process, as in other processes, you know that carboxylic acids are formed at the end, oxalic acid among them. An oxalate forms a complex with iron, ferroxalate, so we noticed that some iron was leached in the presence of oxalic from our diffuser. So now we have changed, and we are using ceramic ones, okay? Well, how to measure ozone in the gas phase? You can use ozone sensors, online sensors, that are based on the absorbance of ozone at 245 to 60, that is where ozone has its maximum. Or you can use the potassium iodide, that is oxidized to iodine by ozone, and then titrate this iodine with thiosulfate. In the case of ozone in the liquid phase, you can also use ozone sensors or, at lab scale, the indigo method. That is based on the oxidation of a dye, the indigo trisulfonate, and measuring the loss of color at 600 nanometers. Let's go back to our system. So we have transferred our ozone. It's working. We have transferred our ozone, and now what? We said that it can act through direct or indirect reaction, molecular ozone, direct reaction of hydroxyl from its decomposition. In fact, we are all both ways are going to contribute always, but the contribution, the higher or lower contribution, will depend on the water matrix, its pH, the presence of inhibitors or promoters or hydroxyl radical scavengers, and also of the external addition of substances or materials or radiation that can improve the decomposition of ozone into hydroxyl. If we design our system in order to improve the decomposition of ozone into hydroxyl, then we say that we are working with an AOP, an advanced oxidation process. So, reactivity of ozone, molecular ozone. Ozone reacts very quickly with unsaturated compounds, with aromatic compounds that are activated, also with amines, more or less, if they are not protonated. But its reactivity towards alcohols, aldehydes, ketones, or carboxylic acid is very low. And this is why when we apply ozone, we do not obtain high degree of mineralization. In the case of inorganics and ions, this is very important because contrary to hydroxyl radical, ozone does not react with carbonate nor bicarbonate. And it not reacts with chloride, sulfate, phosphate, the major anions present in municipal wastewater either. It reacts with nitrite, that is oxidizes to nitrates. And also, as I told you at the beginning, it reacts with bromide, that is oxidated to bromate. With organics, ozone is very selective, reacts with unsaturated compounds, aromatic compounds that have been activated, also amines and several other compounds. In the case of unsaturated compounds, it is through a 1,3 cycloaddition, the Krigi mechanism, is with the formation of an ozonide as intermediate, and also with production of hydrogen peroxide. So here you have some examples of unsaturated compounds with their corresponding direct rate constant, Kd. In the case of organics of aromatic compounds, in the aromatic ring, there are 6 electron-donating groups. They activate the ring to ortho and para position, but if they are electron-withdrawing groups, they deactivate the reactivity of the ring. To see this aspect, see for example, for benzene, the rate constant of its direct reaction with ozone is low, is 2 per molar per second. For toluene, that has a methyl group, it is a bit activated, is 14. For the methoxy group, it's 290. For the hydroxy group, and the anionic form of the hydroxy group. All these compounds activate the ring for the reaction with ozone. On the contrary, the presence of an aldehyde, an halogen, or a nitro group, they activate the ring. If you want to know more about the chemistry of ozone in water, I highly recommend you the book of von Sontag and von Gunthen. It's a really good one. So it is important to know the Kd, the value of the direct rate constant of ozone. Yes, it is, because it allows us to predict the evolution of the pollutants in water when we apply ozone. These values are in the literature for many, many compounds, but in case they are not, we have 2 alternatives. One of them is to use predictive models, QSAR or quantum chemical-based models, or to determine the rate constant experimentally at the lab. So the reaction of ozone is overall second order, first order with respect to its reactant. And even at pH 2, ozone can decompose partially into hydroxyl radicals. So when we determine the rate constant, we have to add an hydroxyl radical scavenger. Normally, terbutanol, but it's not universal. You have to take into account the reactivity, expected reactivity of your compound towards ozone, towards hydroxyl, etc. And also for dissociating compounds, the rate constant changes because the reactivity of the dissociated, non-dissociated species varies. So you have to check also this parameter. When determining the rate constant, you can work in an heterogeneous system. I have worked a lot for many years with Fernando using this method, but I don't recommend it. Yeah. Yeah, because it's more difficult, and at the end there are some uncertainty. So I think that the homogeneous one is better. So in the heterogeneous method, you put in gas containing ozone that firstly has to be absorbed in the water, and then the reaction takes place. You have to take both steps. But if you work in homogeneous phase, you put in contact a solution of ozone in water that is now dissolved with a solution of your compound and the radical scavenger. So if you work following this way, it's much easier. You can use an absolute method, working or not at pseudo-first order conditions, or you can use a competitive method. I don't know if you are familiarized with all this. Well, Marco has talked a bit about that. Well, if you work with the competitive method, use a competitor whose rate constant with the ozone is known. So I'm out of time. So well, this is. So these are the questions to take into account if we work in pseudo-first or no pseudo, etc. Well, are you going to upload the presentations, Antonio? You are going to upload the presentation. Okay, I give you. Well, so we have seen the direct reactions of ozone. The direct reactions are those that they are hydroxyl radicals is involved. So we can, in our matrix, we can have initiator, promoters, or inhibitor. Initiators are those substances that interact with ozone and generate superoxide radical. And the interaction between ozone and superoxide at the end leads to the formation of hydroxyl. Promoter is a substance that reacts with the hydroxyl and generates superoxide radical. The superoxide reacts with ozone, blah, 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 blah. And the inhibitor is this substance that reacts with hydroxyl with no production of superoxide. So the radical chain is stopped. Finished. Yeah. We can enhance the production of hydroxyl combining ozone with other systems. This is, I am sure you are going to see again and again all this system, this combination. But for example, ozone peroxide, hydrogen peroxide, that is the peroxone process, ozone UVC, ozone a catalyst, the catalytic ozonation. I have included the activated carbon, but when you use activated carbon together with ozone, the role of activated carbon is mainly the absorption of the parent compound of the intermediate, not as a really catalyst. Or the combination ozone, UV, catalyst, that is photocatalytic ozonation. And if you use solar light, it's solar photocatalytic ozonation, that is the line that we are following nowadays. So in this system, several different radical species, reactive species are generated that contribute at the end to the elimination of the pollutants. So, I'm finished. No questions. Okay. So, the disappearance rate of a given compound will be given by the equation 17. So the first part of the right hand is the right term is the contribution of direct reaction. The second part is the contribution of indirect reactions. So take into account that the concentration of hydroxyl radicals in water, as Marco said, is going to be very low, much lower than the concentration of ozone, several orders lower. On the other hand, the rate constant of the reaction of the contaminant with the hydroxyl in some cases can be several orders of magnitude higher than for ozone. And this is when a radical is going to attack. So since there are many compounds that react with ozone fast directly, but there are others that not. And also, another good point of ozone is that it not reacts with carbonate-bicarbonate, so the combination of both systems is a really good option. It's a perfect combination. So yeah, the last one. So in municipal wastewater treatment, the use of ozone should be only focused on the elimination of micropollutants or to disinfect in order to reuse the wastewater with different purposes. The operating cost has been estimated to increase up to 35% when ozone is included in the treatment. To be efficient, the development of both reaction pathways, direct and indirect, should take place. And the possible combinations introduced in municipal wastewater is after the secondary treatment, the secondary effluent to be ozonated, or then sun-filtrated, biological sun filtration, or after ozonation, the combination with activated carbon, that is biological activated carbon. And that's all.